Hi, welcome to a quick video introducing finding the equation of the elastic curve, which is our deflection equation. So writing an equation to determine how much the beam is sagging, if you will. And we're going to use the symbol italicized V for our deflection. You might also see Y or capital delta. All those three terms are used interchangeably. There isn't one set term for vertical displacement. And of course, along the way, because we're going to write these equations, we're going to end up finding the slope first. So you can see here we have cantilevered beam fixed at the left side with just a uniformly distributed load W on it, and I've gone ahead and drawn the free body diagram and put the support reactions that are at the wall, so the moment and the vertical reaction. And I've established where we're going to start X, so X will range from 0 to L, starting from the left end. And it's often nice to go ahead and sketch what we think the displacement is going to look like, because that can come back later and help us. So here would be basically the displacement, a bit exaggerated, of as a function of x drawn on the beam. So the first thing we need to do is find our moment expression. And so we know that when we have a continuous load, that we can just have one cut, because we only make cuts where the load is discontinuous, so, or in between where it's discontinuous. So one cut on here, and we can draw our cut. Now, notice I have the support reactions and I have W on here and I've labeled X. The next thing that you really want to do is go ahead and draw the resultant and label it. And remember that when you put that resultant on, it is not WL, because we don't have the entire length L. All we have is the length X. So the resultant is WX, and then it's going to act at a distance of X over 2 from the cut face. And it's really important to mark where it acts, and especially as these beams get more complicated. So take the extra 10 seconds it takes to do that. It will save you time later. And finally, one of the things we also want to put on are the internal forces, so the shear at that length X and the moment at that distance X. And it's really important, I cannot stress this enough, draw them in the positive sign convention. It doesn't matter if you can look at it and know which way it's going to end up going. You always want to draw them in the positive direction. So for the moment on a right face, that's counterclockwise, because it's going to make the beam smile. And we'll see at the very end why it's so important. All right, so now we can actually do a little bit of statics, and we can sum moments at the cut equal to 0. And so when we do that, we would have m of x, we'd have the applied moment WL squared over 2 minus WLX, and then plus WX squared over 2. And then we'll just rewrite that to get the moment expression. Okay, now to move from moment to slope, all we have to do is integrate. And so we want to integrate the m of x equation, and slope is going to be equal to the integral of m of x, but divided by EI, because now we have to get material and geometric properties involved if we're going to see how much is it going to deform due to the loading. So we're just now putting the m of x expression in after the integral. And so when we do integrate that, we'd have our 1 over EI times the quantity WL squared, WLX squared over 2 minus WX cubed over 6 minus WL squared X over 2. And then we have to add in a constant of integration because we don't have boundaries on our integration term. Okay, now that's it. That's our slope expression. If we want to get the displacement, the V of x equation, the equation of the elastic curve, then we just integrate the slope. So let's just write that out. So here is our slope or displacement expression, and so it literally is just the integral of the slope. So when we integrate that, we would have that our displacement is going to be equal to 1 over EI times the integral of WL x cubed over 6 minus WX to the 4th over 24 minus WL squared x squared over 4 plus C1x, because C1 is a constant, so it will now have an x. And then we have to have another constant of integration because this integral also didn't have boundaries on it. So we're almost done, but we have to get rid of those constants of integration. So we're going to use our boundary conditions. And to do our boundary conditions, what you really want to do is just look back at the deformed shape. So I've even put some pictures on of a foam beam deforming so we can see that my sketch is accurate. Where do we know the displacement and the slope? And so if we look at a fixed end, the whole point about something being fixed means it has no rotation. So the slope has to be 0. So we can actually say that at x equal to 0, the slope is equal to 0. And so if we start plugging that in, we'll just have 0 plus 0 plus 0 plus c1 equals 0. Probably should have been 0 minus 0 minus 0 plus c1, but it's 0. It doesn't matter. And then when we also look at the displacement, you could say, well, I know it's maximum at the free end, but I don't know the magnitude of that. And without a magnitude, that does not help me find constants of integration. But we do know its magnitude at x equal to 0, and it is 0. So we can plug that in, and we'd again get 0 is equal to 1 over EI, and then we'd have this 0 plus 0 plus 0 plus 0 plus C2. So cantilevers are great because our C2 is also equal to 0, which means we can now simply write out the solutions, and it's just rewriting the slope expression and the displacement expression. So just recopying that without the C1 or the C2 in it. And so now you could plug in any value from 0 to L and know what the displacement is at that exact point, which is really exciting, or what the slope is. Now by observation, we can definitely say that the max is at L, so let's just plug that in and see what we get. And so when we solve these fractions, we're actually going to end up with negative WL to the 4th over 8EI. And that's important that that comes out as negative because it tells us it's going down. If we had drawn our m of x on the cut way back at the beginning, going clockwise instead of counterclockwise, we would have got a positive answer for our displacement at the free end saying that it's deflecting up. And we know it's not doing that. And so that's why it's so important. Always draw it in the positive direction so that the displacement equation will give you the proper signs. Hope you enjoyed this video, and we're going to start getting into discontinuous loadings as the class continues. Thanks for watching.